Let us discuss about work and heat transfer by Dr. H.V. Mulimani, working as Assistant Professor in Department of Mechanical Engineering in BGMIT, Mudol. Let us try to understand work and heat transfer. A closed system and its surroundings can interact in two ways, that is, by work transfer and heat transfer. So let us try to understand about the work transfer, and then in later slides we can study about the heat transfer. The work is done by a force as it acts upon a body moving in the direction of the force. So in mechanics, the work is defined by the force applied on the distance moved by the object. So work is defined as the product of force and the distance moved in the direction of force. So this is as shown in the figure. Let F be the force applied on the body. 1 is the initial position, 2 is the final position. Okay, so now as the body moves a small distance, say dx, and let theta be the angle between the force and the displacement. So work done in mechanics is nothing but the product of force into distance moved. So work done is equal to F into dx. If it is moved by some angle, then we introduce the cos theta. So F into cos theta into distance moved dx. So on integrating from the initial and the final point, that is from 1 and 2, we get F into cos theta into x2 minus x1. This is the force applied into the distance moved with some angle. If there is no angle, it is a horizontal force, then F into dx. Okay, so this is how we define the work in the mechanics. The main limitation of this work in mechanics is work cannot be calculated without the actual movement of the load. According to the definition of work in mechanics, the force or the load and the action of this force through a distance are necessary. So we cannot calculate the work if there is no movement. That is the main limitation of the work defined in the mechanics. In previous slide, we have understood the work according to mechanics. Now in this slide, let us try to understand the work in thermodynamics. In thermodynamics, work transfer is considered as occurring between the system and the surroundings. With respect to thermodynamics, work should be having the concept of system, properties and the processes. So let us try to define the work in case of thermodynamics. It is defined as work is said to be done by a system with the sole effect on things external to the system, that is surroundings, can be reduced by the rising of the weight. So according to definition, the weight may not be actually raised, but the net effect external to the system should be the rising of the weight. Therefore, in case of thermodynamics, definition of work is more general than it was defined in the mechanics. Let us try to understand the above concept by the figure. Consider the figure A, where the battery is attached with the resistance coil. The battery is our system. When the switch is closed, the current flows through the resistance coil and it gets heated up and thus heats the surrounding. Due to this, the battery charge decreases. Even though there is an interaction between the system and the surrounding, but according to the mechanics, no work is done because there is no displacement in this system. So now let us consider the figure B. In this figure B, the resistance is replaced by the motor. The motor draws the same amount of current as the resistor, and the motor is attached with the pulley and the weight. When the switch is closed, the motor runs and the weights are raised. Now, hence the sole effect external to the system has been reduced to the rising of a weight. Hence, according to the definition of work in thermodynamics, this interaction can be called as work, though actually no weight has been raised through any distance. Sign convention for the work. The figure shows the sign convention for the work. Now, work done by the system is taken as positive. Work done on the system is taken as negative. The figure is actually a self-explanatory, and in the PV diagram, work is considered as positive if we move clockwise around the closed area, and is considered as negative if we move in the anti-clockwise direction. Displacement work or PDV work. It is also known as work done in a frictionless quasi-equilibrium process. Consider a system in thermal equilibrium in a frictionless piston and cylinder arrangement as shown in the figure. At initial state 1, the gas is represented by P1 V1. Now, since it is a quasi-static process, let us remove a small weight from the piston. There will be a small drop in pressure on the gas. The gas undergoes a little bit of expansion. Hence, it moves a small distance, say dx. In this, let assume that P is the pressure on inside the piston, dx is a small distance moved, A be the cross-sectional area of the piston, small d be the diameter of the piston. So work done is given by force into distance moved. So as we all know, pressure is F by A, that is force per unit area. So F can be written as F is equal to pressure into area. So work done is equal to pressure into area of the piston into the distance moved, that is P into A into dx. Now the area and the small distance dx can be written as volume. So area is meter square and dx is m. So it will be meter cube. So the delta W is equal to P into dV. Now, if the piston moves through a small finite distance, the work done by the piston is obtained by integrating the above equation between the initial point and the final point, that is from the point 1 and 2. Hence, the work done from 1 to 2 is given by integration of from the limit 1 to 2 into P into dV. So that is the displacement work or the PDV work. PDV or displacement work for various quasi-static processes. In this we will be referring to constant volume process, constant pressure process, constant temperature process, and lastly polytropic process. In constant volume process, that is isochromic process where volume equal to constant, constant pressure process, that is isobaric where P equal to constant, constant temperature process where it is also known as isothermal process, PV equal to constant. Lastly, the polytropic process where PV raised to n equal to constant. Let us consider constant volume process where V equal to constant, that is V1 equal to V2. So work done is given by area under the curve 1 to 2. So work done is nothing but integration of PDV, integration of 1 to initial point to the final point. So P in when after integration P into V2 minus V1. So here since the volume is constant, it is a constant volume process, isochromic process. So we have V2 equal to V1. So work done is equal to 0. Now coming to the next constant pressure process, that is isobaric, pressure equal to constant. So work done is equal to area under the curve 1 to 2. So work done equal to the limit of initial position to final position 1 to 2 PdV. So P into V2 minus V1. So work done for the constant process is P into V2 minus V1. Constant temperature process, that is isothermal process where PV is equal to constant. So as similar to before what we have done, work done is equal to area under the curve 1 and 2. So we already know work done is equal to integration from initial position to final position PdV. Now since PV equal to constant, we can write it as PV equal to P1 V1 equal to constants. Hence P is equal to P1 V1 by V. So we can replace the Py P1 V1 by V. I have indicated in the arrow mark also for our better understanding. So work done is equal to integration of initial position to final position 1 to 2 into P1 V1 by V into dV. So after integration we get work done is equal to P1 V1 ln of V2 by V1 or P1 V1 ln of P1 by P2 because P1 V1 equal to P2 V2 equal to constants. Hence V2 V1 can be replaced by V2 by V1 can be replaced by P1 by P2. Hence work done at constant pressure or isothermal process is given by P1 V1 into ln of V2 by V1 or P1 V1 ln of P1 by P2. Polytropic process. So work done is area under the curve 1 to 2. So polytropic process is PV raised to n equal to constant. So work done equal to PdV. So we are replacing P is equal to P1 into V1 by V raised to n. So for integrating under the limits 1 to 2. So P1 V1 raised to n, so that into V raised to minus n plus 1 divided by minus n plus 1 up to the limits b1 to v2 because integration of x raised to n dx equal to x raised to n plus 1 divided by n plus 1. So here our n is minus n. Okay, so I am replacing n with minus n. V raised to minus n plus 1 divided by minus n plus 1. So substituting those limits and after that P1 V1 raised to n equal to V2 into 1 minus n minus V1 raised to 1 minus n divided by 1 minus n. So individually multiplying with their initials, so we will be getting 1 we have P2 V2 raised to 1 minus n plus 1 plus n minus P1 V1 1 minus n plus 1 n. So n gets cancelled. We are left out with P2 V2 minus P1 V1 divided by 1 minus n. So I want the P1 V1 minus P2 V2. So it will be 1 minus n will be replaced with is changed with n minus 1. So work done for the polytropic process is P1 V1 minus P2 divided by n minus 1. Free expansion process or no work transfer. We all know that work transfer is a boundary phenomenon. That is, it is identified at the boundaries of the system. Now, consider a gas separated from vacuum by a membrane partition. Let both gas and vacuum form a system as shown in the figure with a dotted line, and it's filled by a light blue color, and the green color is a insulation, and there is a partition which is of membrane or any other thing. Okay. Now if the partition is removed, the gas will fill the entire volume, and this expansion of gas against the vacuum is called as free expansion. If work required of removing that partition is neglected, then no work transfer is involved as no work crosses the boundary. Hence, work done is 0. But PdV from initial position 1 to 2 is not equal to 0. Now, consider only the gas is taken as a system as shown in figure by a dotted line filled with a light blue color. When the partition is removed, there is change in volume of gas. But this is not a quasi-static process, whereas initial and final positions are in equilibrium. Hence, they are indicated by the dotted line from 1 to 2. Therefore, what cannot be calculated by integration of PdV, that is PdV. This can be made a quasi-static process by dividing the vacuum into smaller partitions, and then the gas can be expanded by removing each partition one by one. Then every state will be in a equilibrium, and work done can be calculated by PdV. As in vacuum, gas will not face any resistance as as the gas starts to expand in the vacuum space. Since vacuum does not offer any resistance, there is no work transfer involved in the free expansion. Let us consider other types of work. Electrical work. When a current flows through a resistor, when we consider the resistor as a system, when the current flows through the resistor, there is a work transfer into the system because the current can drive the motor and this motor can drive the pulley and this pulley can lift the weight. So the current flow I, which is given in ampere, I equal to current equal to dc by dt, where C is the charge in coulombs and T is the time in second. So we can rewrite W as integration, that is 1 to 2 E into DC, where E is the voltage potential and DC can be replaced by I into dt. So work done equal to E into I. The other type of work is shaft work. It is as shown in the figure. When a shaft, which is considered as a system, is rotated by a motor, there is work transfer into the system. If T is the torque applied and d theta is an angular displacement of the shaft, then the shaft work is given by W is equal to T into d theta. D theta is nothing but theta, theta 2 minus theta 1 in kilonewton meter. And the shaft power is given by W is equal to T into omega, where omega is the angular velocity. Now considering the stirrer or pedal wheel work, the other type of work. The pedal wheel work or steering work is as shown in the figure. As the weight is lowered, the pedal wheel rotates. Hence, the work is transferred into the system. But here, since the volume is constant, the work done is PdV, that is equal to 0. If now the m be the mass of the weight lowered through a distance dx and T be the torque applied to the shaft, then by rotating it with the angle theta, the work done is given by mg into dx, which is nothing but T into t theta. The other type of work transfer is work in changing the area of the surface film. Here, the surface tension acts to make the surface area of the liquid minimum. A film on a surface of a liquid has a surface tension, which is a property of the liquid and the surrounding. Here, the work is given by integration of 1 to 2 surface tension into the small surface area. So here the sigma is denoted by the surface tension, which is having the unit Newton per meter. The other type of work transfer is magnetization of a paramagnetic solid. Here the work done is given by integration of product of H into di, where H is a field strength, I is a component of a magnetization field in the direction of the field. After understanding the work transfer, let us deal with the heat transfer. Heat is also a form of energy which transfers across the boundary by the virtue of temperature difference. There are three modes of heat transfer, that is by conduction, convection and radiation. And heat is transferred from higher temperature to the lower temperature. For example, if you have a cup of tea, the heat transfer takes place from the cup of tea to the surrounding unless the system and the surroundings be in equilibrium, that is it reaches the same temperature as the surroundings. The heat transfer solely occurs because of the temperature difference between the two systems. Hence, heat is a transient phenomena. The temperature difference is a cause or a potential, and the flow of heat is called as flux. Now coming to the sign convention, it is just opposite to the work transfer. Heat flow into a system is taken as positive and the heat flow out of the system is taken as negative. The symbol commonly used is the Q for the heat transfer. After studying the work transfer and heat transfers, let us do some comparison between the heat and work. Now first let us see some similarities. Both heat and work are energy interactions. That is, as we all know, in a closed system, the energy can interact with the surroundings in two ways. That is, by heat and work. Hence, heat transfer and work transfer are energy interaction. And one more similarity is both are transient phenomena as they exist during interactions only. Both heat and work crosses the boundary when a system undergoes a change of state. And it is always wrong to say total heat or total or heat content of a closed system because both the heat and work can't be stored by the system. And we all know both heat and work, which are energies, they occurs at the boundary. So both are the boundary phenomena. And as discussed in the previous sections, even both are the path functions. These are some of the basic similarities between the work and the heat. Now let us study the dissimilarities between work and the heat. Heat transfer is an energy interaction due to only the temperature difference, whereas the work is not. That is, energy interaction other than temperature difference is called as work. Work is a measure of organized and directional flow of energy, whereas heat transfer is a non-organized flow of energy. The other dissimilarities is conversion of heat to work is less, whereas conversion of work to heat is more. Hence, we can say that heat is a low grade energy, whereas the work is a high grade energy. These are some of the dissimilarities, and we can add even the sign convention of our work and heat. The work done by the system is the positive. Work done on the system is negative. Whereas heat flows into the system is positive. Heat flows out of the system is negative. These are some of the dissimilarities between the work and heat. Thanks for watching.